Okay, so last time, if you remember, we derived one of the important and relatively sort of simple partial differential equations that you can study, which is called the transport equation. And so remember, what does this equation say? Well, maybe you have a pipe with water flowing through the pipe, right? Maybe water is moving to the right, and you have some pollutant that's placed in the water. And so the equation describes how this kind of maybe foreign object moves through the pipe, right? And so say the water moves at speed c, and we're in the, let's say it's moving horizontally, so let's say it's in the x direction, right? And so if we let u of xt, this function of u, equal the concentration of whatever this pollutant is at time t and position x, right, just as some quick review, where x is along the x-axis or along the direction of the pipe, then we derive the following equation, which gives an approximation for what's going on or describing the physical system, which is if you take the time derivative of u, then this has to be proportional to the x derivative of u. And the constant of proportionality is basically just the speed that the water is traveling. So the negative of that. And one way of rewriting that is if you, instead of writing it ut as some constant times ux, you just move over the term involving the x derivative, and you get this first order linear equation, right? And so this is what's known as the transport equation. And we derive this just from basic principles. Remember, if you look at a tiny piece of a tiny section of the pipe, well, if the water is moving to the right at speed c, you expect everything in that section, if you let time change a little bit, is just going to move over proportional to this rate of speed. And so if you write down what this means mathematically, you can derive this equation as we saw last time. So what I want to do is just look at one example of a particular solution to this equation. Remember that in the last lecture, we spent a lot of time talking about these types of PDEs, so we know how to solve them, right, using this method of characteristics. So let's just look at a quick example and see what the solution looks like, and see if this matches what you would expect from your physical intuition about what's going on here. Right, and so for this example, let's suppose U is a solution to the transport equation. And suppose that we know that when time is equal to 0, right, let's say when, I don't know about x, but when t is set equal to 0, we know that this function, which basically, well, when t is equal to 0, you want to think of this as the initial state of the system, and then as t grows, the system is changing over time. So this is kind of what it looks like at the starting point. Let's say this is the function e to the minus absolute value of x, at least in whatever domain you're looking at. Right, and so we know how to solve, right? Because this is just a first order linear equation. And so we have a formula. In particular, there's constant coefficients, so we can just use the formula without having to worry about like the more complicated case where you have to solve an ODE or something like that. And so the solution is just, we know that u of xt is equal to some function f of x minus ct, where the c just comes from looking at the coefficients. Right, and so now we can use the initial condition to figure out what f must be, right? So then, well, if I set t equals 0, that has to equal e to the minus absolute value of x. But if I set t equals 0 on the right-hand side, I just get f of x, Right, and so my function f has to just be e to the minus absolute value of x, and therefore I now know what my solution looks like, right? So u of xt, I just plug in x minus ct to f, so it's e to the minus absolute value of x minus ct, right? And so this is my solution. So there's one technical point which is maybe worth pointing out. So if you remember, absolute values cause issues with taking derivatives at a single point, right? So the point where they make a corner. So this function is actually not differentiable when x is equal to ct. Right, because at this point, if you take the derivative from one direction, the slope is going to be different from another direction because there's going to be a corner. So it turns out that for the sake of a lot of applications, even if your initial data looks like something like this example where there's maybe not a derivative at certain points, there are ways around this issue where you can maybe approximate it very closely by something which has derivatives, or you can define the PDE in a different way in order to deal with sort of rougher data or not things that are called like non-smooth initial conditions. So for this class, we're just going to sort of assume that, well, if there's only a few points where the derivative doesn't make sense, maybe there's an issue at that point, but everywhere else, this function gives an accurate description of what's going on, and you just can't take the derivative at one point, but otherwise it's still okay. Right, so even though the function is not differentiable at this one point, we're not going to really worry about that issue too much. And if you take more advanced partial differential classes in PDEs in the future, you'll see how to get around this issue. And maybe we'll talk about it a little bit near the end of the semester as well. So ignoring this minor technical point, what does the solution look like? Right, so let's first draw say this is the x-axis. Remember U measures the concentration, right? So let's first look at, say, t equals 0. Well, the function looks something like this, right? Where it kind of peaks at the origin, right? Because when t is equal to 0, I just have e to the minus absolute value of x. And so that's basically what this looks like, or what this is the graph of. Maybe let me, right? Okay, now let's see what happens when t is equal to 1. Let's use a different color for that. When t is equal to 1, well, if I plug that in, my function is now e to the minus absolute value of x minus t, rather than just absolute value of x. And so if you look at this, well, remember the peak in the original function is when x is when the term in the absolute value is equal to 0, right? Because that's when the exponential is the largest. And so now when t equals 1, oh, sorry, it should be x minus c, not x minus t, excuse me. Great, so now when t is equal to 1, the peak is going to be when x is equal to c, right? So maybe this is c over here, and so now the peak has moved, and so the graph is going to look something like this, right? And so my concentration has moved to the right at this speed. And maybe let's do one more time. Let's say maybe t is equal to, say t is equal to 3. Right, and then, well, I plug in t equals 3, my solution is e to the minus absolute value of x minus 3c. And so now the peak is going to be when x is equal to 3c. And so let's draw this. Maybe we just have to extend the axis a little bit. Right, so maybe this is c, maybe 3c is around here. And so at time t equals 3, let's say 3 seconds or something, it's moved. So the solution looks like this. Right, and so it's moved this amount. And so you can see like a relatively simple model of the phenomenon we described before, because the concentration is moving to the right at the speed that you would expect, right? In 1 unit time, it moves a distance about c, which essentially means it's traveling at speed c. And so this turns out to be, again, a pretty accurate description of what's going on if the pollutant is like a solid object, right? However, if the pollutant is like some kind of like chemical or dye or something, you would expect it to spread out also, and we're not seeing that phenomenon here. So in order to capture that type of phenomenon where something is spreading out, the equations are more complicated. And so this is related or will involve something called diffusion, and we're going to look at the diffusion equation near the end of this lecture. And so there are more advanced versions of the transport equation that take into account diffusion also, which maybe we can talk about in the future. Okay, and so, but for now, that's everything I wanted to say about the transport equation. And so the next thing we're going to look at is the derivation of the wave equation. Right, and so we've looked at the wave equation a little bit, but just kind of abstractly, I just wrote it down and told you what it is, and used it as an example for some of the stuff we talked about in the first lecture. And so now what we'll do is actually explain, well, where does this equation come from, and how do you derive it? And so the basic starting point is to consider maybe a vibrating string, which you can think of as looking like sort of like a wave. Say, right, so I'm going to use, again, I'm going to look at this in a one variable or two variable situation, and then we'll talk about more general versions of it afterwards. So let's say I have the x-axis here, and say I have a string starting at 0.0 and ending at 0.1, and maybe the string kind of oscillates a little bit like this, right? And so imagine this is like maybe like a guitar or like a violin string, right? And so it's been, let's say, plucked or pulled like this. And then what you're going to do is release it, and it's going to oscillate up and down over time, right? So when it's released, it oscillates up and down. And so it's going to turn out that this PDE, known as the wave equation, describes this type of motion. And so how are we going to make this a little bit more precise? So we're going to define a function, which will be a function of x, which is the coordinate on the x-axis, and then also time, t, which you'll think of as time. And so I'm going to let this be the displacement of the string in the y direction. So y is the vertical direction. At point x and time t. Right, so at point x on the x-axis and time t. Right, and so let's say this is my point x. Well, the function u measures how big this displacement is at time t. So this would be u of xt. So u of xt lands on the y-axis, right? So maybe this is like x1, and maybe this is x2, and over here the displacement is going to be negative, right? So u of x2t would be down over here, like over here, right? And so so this is at some fixed time t, but I mean, think about it, as the time changes, the string is going to be moving up and down, so then the displacement changes as well, right? And so that's what this equation will measure. Right, and so what is the claim? So the claim is that u is a solution to what we call the wave equation. So the claim is that if I take the second derivative of u with respect to t, that this has to equal some constant c squared times the second derivative with respect to x of this function, where c is a constant. Right, and so this is what we'll show, right? So, right, we're going to derive this equation, and what we're going to do is derive it in a slightly simplified context, which will help indicate exactly what this constant is. So we're going to begin by making some physical assumptions. In particular, we're going to make two physical assumptions about the string, just to simplify matters, right? right? And so the first assumption is that the density of the string is fixed or constant, and say it's equal to some number, which is the Greek letter rho. I'll use that for the density, and also the tension of the string, which is kind of related to the how much the string how much force the string has when it's being pulled or something like that. Right. So the tension of the string will be, again, related to the force that affects the motion, is going to be also constant. Sorry. Right, so the tension will be constant and equal to, let's say, tau, or the Greek letter tau, which will just be a stand-in for the word tension. And so, of course, in the real world, when this is actually applied to solve real world problems, the density is not necessarily constant and the tension is not necessarily constant. But in order to understand the more complicated scenarios, you first have to look at the easier scenarios where you have like the most basic physical assumptions. So that's what we're going to do here. And so in this case, well, the constant c, we'll see, is going to be given by the square root of the ratio of these two things. So in this case, you'll have c squared is equal to tau over rho, and we'll see why later on. Okay, and so as I mentioned in the last lecture, I'm going to do a derivation of this equation, which is a little bit different than what's in the textbook, because I think the derivation in the textbook is maybe just a little bit too fast for people who don't have more experience with these types of problems in physics. And so I'm going to use a different derivation, which I think also introduces some other interesting concepts and techniques which are useful, which will be useful later on in the course. And so before we turn to deriving the equation, there's just one mathematical fact which I want to review, which we're going to use. And so this is a property related to second order derivatives, which you'll expect is relevant because both the derivatives in time and in space are second order for this equation, which maybe some people have seen before, maybe some people haven't. So I'll review it and prove this fact, right? So let's say we have a function, say f of x. And suppose f we know that we can at least take 3 derivatives, right? So at least 3 times differentiable. This is kind of a technical assumption, which you can ignore, but I just want to have it here for completeness. Right, and so what is the property we're going to use? Well, it's a way of writing the second derivative of f as some kind of more complicated second order difference quotient. So I can write the second derivative of my function f as the limit as h goes to 0. In the numerator, I'm going to put f of x plus h plus f of x minus h, and then you have to subtract off 2 times f of x. And then in the denominator, I'm not going to put h, but instead h squared. Right, so when you look at this, you want to think of the limit definition of the derivative. So it turns out there's a version of that formula for second derivatives, but it's a little bit more complicated, and that's what this fact is. Okay, and so why is this the case? Let me prove it. So what we're basically going to do is just use the Taylor expansion of the function. Right, so I'm going to look at the Taylor expansion at x plus h and also at x minus h. So I'm going to get 2 different formulas, which I'll combine to get this result. Right, so if I do a Taylor expansion about x plus h, well, I could write my function f of x plus h as, or sorry, I guess, right, maybe let me just write out the formula, and you could, depending on how you learn this, right, yeah. Anyway, right, so if I do a Taylor expansion, I can write f of x plus h as f of x plus h times the first derivative at x, right, where h is the displacement or the change between the point on the left and point on the right. Well, then I have the second order term, which is the change squared. So h squared divided by 2, right, times f prime prime of x. And then it keeps going, the Taylor expansion. So I have third order terms, right? So I'll have like h cubed over 3 factorial times other terms, right? And so the Taylor expansion keeps going and you keep getting larger powers of h. But since we're going to view h as very small, right? We're taking limit as h goes to 0. It's going to turn out these terms will be negligible. So I'm just going to write h cubed times the rest. Right, and so let's write out the same formula now for f of x minus h. So it's going to look exactly the same, except now we get a minus sign in front of h. So this is f of x, and now we have minus h f prime of x. Well, if I take negative h squared, it's just h squared again. So we get that. And then we have now minus h cubed over 3 factorial times, right, the other terms. Okay, and so now if we go back and look at what I'm trying to prove, it involves adding these two things together, right? Adding f of x plus h to f of x minus h. So let me do that. So therefore, if I add these together, this is equal to, well, I get 2 times f of x from adding the, right, just combined like terms, right? So 2 times f of x. The first derivatives cancel because notice for one I have positive h and one I have negative h, so those cancel. And then if I add the second derivative terms, well, I get h squared over 2 plus h squared over 2 times f prime prime, right? And then I have the terms involving h cubed, right? So I'm just going to write this times, right? And so if I simplify this, well, what do I get? I get 2 times f of x plus h squared times the second derivative, and then plus the negligible terms. Right? And so now I'm almost done. So let me just rearrange things. So if I subtract 2 times f of x, I get f of x plus h plus f of x minus h minus 2 times f of x is equal to h squared times the second derivative plus h cubed times the other terms. And so now if I divide by h squared, right, well, this is going to, well, right, so the term in front of the second derivative cancels out, and then I have h cubed divided by h squared times the rest, which turns out to be h. And so now let me finally, we're almost done, so let me finally write this as right, so the difference quotient on the left-hand side is equal to the second derivative of f plus h times what are called like higher order terms, or it's like small error terms. Right, and so now if I let h go to 0, the error term is going to converge to 0 because I'm multiplying something that's converging to 0 times the rest. And all these things are like different powers of h times like fixed numbers. So there's no issue with like maybe the h gets canceled out. It doesn't happen. So the error goes to 0. And so this proves the result, right? Because on the left-hand side, I'm going to take the limit of this complicated difference quotient, right, which is what we were looking at here. And then on the right-hand side, I have just the second derivative of f plus something that's going to 0. And so that proves the result. Right, so that's the end of the proof. Okay, and so this quotient we'll see is going to turn up when we analyze this the system that we're looking at, and it's going to be the reason that the second derivative with respect to x will show up. Okay, and so now let's turn to the actual derivation of the equation. Okay. And so the main idea which turns out to be a very useful idea, especially in applied math and engineering and things like that, is you have this continuous system, which is the string that is oscillating up and down. And what we're going to do is approximate the string by a lot of different, view it as like a combination of a lot of different tiny particles, right? So we're going to approximate the string by, say, like capital N, where capital N is going to be a very big number, by n masses or particles. Right, and so the idea is, well, maybe your string looks something like this. Well, here's my x-axis. And so what you can do is think of it as like maybe linearizing. Like I can take like a block here and a block here and a block here. Right, and maybe this gives me a good approximation of what the string looks like. Right, so I'm gonna kind of discretize it or view it as like a slightly simpler, more linear thing. So maybe I'm going to approximate my string by something that looks like this. Right? Right, and say I have some particle y. Let me just label these. Right, say this is like point xn, fix some point, and maybe this is point xn minus 1. This is point xn plus 1, and so on. Right? Right, and so what we have again is we have this smooth or continuous curve, and what we're doing is maybe breaking it up as and viewing it as like a combination of some large number of discrete things. And so as you let, right, so n is going to be the number of particles, and as n goes to infinity, you get a better and better approximation of what the string actually looks like, and then in the limit, you're going to recover the full string, right? Right, and so, right, so how are we going to do this a little bit more precisely? Well, we're going to choose our points xn so that they're separated by distance h. Right, so I didn't draw this exactly to scale, but I'm going to assume that these are separated by distance h, where h is going to equal 1 over n. Right, and so as n goes to infinity, you get more particles that are closer together, and again, you recover this continuous string from this discrete picture. Right, and so, right, and so just to make this description more precise, what we're going to do is, right, so we're going to decompose, say, the interval between 0 and 1, which is on the x-axis, into intervals of length h, which is 1 over capital N, of the form, like say, xi comma xi plus 1. And so I'm also going to let yi, which I'm going to view as this particle, it'll depend on t. It's just going to equal my function, or the displacement, u, at point xi in time t. Right, so this is the displacement at xi and time t, exactly as we defined u before, but now we've just kind of discretized it and we're only looking at finitely many points instead of the whole interval, right? Just somewhat simplifying it. And so in particular, notice that if I return to the diagram I have drawn up here, well, this means that if I look at xn minus 1, since the gap is exactly distance h, that means xn minus 1 is xn minus h, and xn plus 1 is xn plus h, right? So I can get from xn minus 1 to xn by increasing by h, and I can get from xn plus 1 to xn by decreasing by h, right? And so when you see these formulas, you should think of this calculus fact we looked at above. And so what we're going to do is relate these quantities together in some way, and this quotient is going to pop up, and we'll be able to use this to get the second order derivative to appear. Right. Okay, and so this is maybe the approximation or mathematical, the basic kind of approximation or mathematical framework that we're gonna look at the problem in. And so whenever you're deriving equations like this, there's always going to be some point where you have to input some data from physics or some physical ideas, right? So the math is only going to bring you so far. And so what we're going to do is write down two separate physical assumptions about the system that we can derive from basic physical principles. Right, so the first assumption, right, and so the first assumption is going to be related to the fact that we're assuming the string has constant density. And so the assumption will be that each particle yn has mass exactly equal to rho times h, or like, remember h is 1 over n, so rho times 1 over n. Okay, and why is this a reasonable assumption? Well, recall that the string has constant density, right? So it has density rho. And remember, the density is just the ratio of like mass, in this case, to unit length, right? And so if you're looking at an interval of length h, you would expect that the mass in that interval is about rho times h, right? So an interval of length h, we expect that the mass of the string to be approximately rho times h, where the approximation is better as h goes to 0, right? Or better approximation as h goes to 0. And that's exactly the scenario we're in here, right? So I have, for example, right, I have my yn, say we're looking at particle yn. Well, this is above xn, and then maybe, just to remind myself, right, so maybe yn plus 1 is down here. Well, this interval between xn and xn plus 1 is exactly h, right? So we're in exactly the scenario I described. And so it's reasonable to assume that each of these particles has mass about rho h, right? Again, just because it's really just the fact that density is mass divided by unit length or whatever. Right, and so that's the first assumption we're going to use. And then the second assumption is related to how the particles act on one another, like the force that these different particles apply to one another. And so to understand this a little more, let's just return to the picture for a second. And so if you look at this picture, well, let me erase these just to give room. Right, you can imagine that this particle yn minus 1 is maybe pulling yn downwards. Right, and also yn plus 1 is maybe pulling yn downwards. Right, and so what we're going to assume is that only the neighbors of a fixed particle act on it, right? So maybe yn will act on yn plus 1, and maybe yn plus 2 will act on yn plus 1, but nothing else, and so on, right? So we're going to assume, right, so this will be physical assumption 2. Actually, let me put this up here. We're going to assume that the force on particle yn is due to the effect of only its neighbors. So there's going to be some component of the contribution that comes from yn minus 1, and another contribution that comes from yn plus 1, right? And so in this simplified model, this is a reasonable assumption. In reality, it's not actually true. But in reality, you're going to, if you look at like what's actually going on, the equation will be more complicated than the wave equation we're working with. Again, this is a more simplified model. Right. Okay, and so what we're also going to, right, so now we know that the whatever force is acting on, let's say we fix the particle yn, whatever force is acting on it is only contributed from its two neighbors. And so let's try to understand what these forces should actually be if we write down equations for them, right? So what's a good candidate for the force due to yn minus 1, which is the particle to the left, right? Maybe to have a picture of what's going on here. So like this is yn minus 1, this is yn plus 1, and so on. Right, and so this is the situation where this constant that's related to the tension of the string is going to play a role, and so we expect. So we're going to assume that the force of yn minus 1 on yn is proportional to, well, basically kind of like a difference quotient where I look at, say, yn minus 1. I consider the difference or the change in the displacement, and I look at that relative to the length of separation. So I look at yn minus 1 minus yn divided by h. And so then the force due to yn minus 1, we'll assume it's proportional to this ratio, and the constant of proportionality is going to be the tension of the string. Right, so if the string has a lot of tension, there's more force, and if the string doesn't have a lot of tension, there's less force, which is a reasonable assumption, and we're assuming it's kind of like a linear thing in the tension. So the force due to yn minus 1 is going to be equal to tau, which is the constant related to the tension, times yn minus 1 minus yn over h. Right, another way of writing this is tau divided by h times yn minus 1 minus yn. And so if you think about this formula for a second, why is this a reasonable way to describe the force? Well, imagine h is very small. So if the difference between yn minus 1 and yn is very large, you're dividing a large number by a very small number, so the ratio is going to be large, which means that if these particles are close in terms of the x coordinates, but the displacement is far apart, that means that you would expect that one is kind of pulling very heavily on the other, right? On the other hand, if they're kind of close together, if the displacement yn minus 1 minus yn is relatively small, right? So maybe, right, so then you would expect there not to be too much force. So maybe it helps if I draw a picture, right? So in our scenario, I have like yn minus 1 here and yn is here. So in this case, there's a lot of displacement or separation between them, right? So you would expect like a larger force. On the other hand, maybe if I drew the picture differently and maybe yn minus 1 is here and yn is only just a little bit above that. And so in this case, the displacement is relatively tiny. So it's just like this. So you would expect there to be a smaller force. And when I say larger or smaller, I mean really in terms of the magnitude, right? So force also has a directional component, which will just correspond to whether or not this quantity is positive or negative, right? Right, and so we'll now have a similar formula for the force due to yn plus 1. We'll just use the same idea. So we're going to assume that the force due to yn plus 1 is, again, this tension coefficient tau divided by h, where, again, h is the separation of the input, and then times yn plus 1 minus yn. Okay, and so these are our two main physical assumptions, right? So we have this assumption about the mass of each particle, and then we have this assumption about how to describe the forces acting on a fixed particle. And so when you think of force and mass, this should remind you of Newton's second law. And so we're going to tie these two together by using Newton's second law of motion. This is actually a common tool technique in a lot of these derivations. Right, so now by Newton's second law, well, what does that say? Remember, it says that the force in a system is equal to the mass times the acceleration, right? Well, what is the force? So in this case, our force on, let's say I look at yn of t, right? So we're looking at one fixed particle for now. Well, we're just going to add the two contributions from yn minus 1 and yn plus 1. So it's equal to, well, I have tau over h times yn minus 1 minus yn. This is from the particle to the left. And then I have the contribution from the particle to the right. Right, so that's the force. And then this should be equal to the mass of yn times the whatever the acceleration is of yn. Well, we know what the mass is from the first physical assumption. The mass should be rho times h, right? So I have rho times h. And then what is the acceleration? Well, the acceleration is like how related to how it's changing with time or moving with time vertically, right? How the displacement is changing. And remember, acceleration involves second derivatives, right? So this should be the second derivative of y with respect to t of yn, right? So we get this formula. Right. And so this is kind of like the discrete, what I'll call discrete wave equation, which is describing the system of particles before we take any limits. Right, so there's no limits here, just viewing it again as a system of n particles. Now we're going to take limits and we're going to recover we'll see we'll recover the original equation. In order to do this, let's first like plug in, right? So if I just write it like this, maybe it's not exactly clear what we should do, but let me just, when you're stuck on a problem like this, it always helps to just plug in as many definitions as you can. And so what does this equation actually say? Well, recall that yn of t, well, we define this to be my displacement function u evaluated at xn at time t. And similarly for yn minus 1, right? Yn minus 1 is u of xn minus 1 of t, etc. So let me plug in these definitions and simplify, right? So on the left-hand side, you have, well, I have tau over h. If I combine these terms, I get yn minus 1 plus yn plus 1 minus 2 times yn, which is now equal to, if I plug in u, well, I have u of xn minus 1 at t plus u of xn plus 1 at t, and then minus 2 times u of xn at t. And well, if we recall, well, remember xn minus 1 is just equal to xn minus h, and xn plus 1 is equal to xn plus h. So I can simplify this further as tau over h times u of xn minus h at t plus u of xn plus h at t, and then minus just twice u evaluated at the point xn. Right. And then on the right-hand side, what do we have? Well, if I just move this up a little bit, you can see we have, well, we have rho times h. Rho is the density constant. H is just this separation parameter. And then we just have the second derivative with respect to t of u evaluated at the point xn at time t, right? And so this is why this is kind of like the second order, or the discrete version of the wave equation, because on the left-hand side you have this this difference quotient, which looks a lot like the second derivative we calculated up here using the Taylor series approximation. And then on the right-hand side, you have the second derivative with respect to t. Right, and so finally what I'm just going to do is set these equal to one another and then divide by h, right? So then it follows that if I just do a little bit of algebra, I get on the left-hand side u, just bear with me while I kind of rewrite things in a simplified way. I get u of xn minus h, comma t, plus u of xn plus h, comma t, minus 2 times u of xn t, divided by h squared, is equal to, well, I'm going to move all the constants over to the other side. So it's equal to rho divided by tau times the second derivative of u with respect to t at xn at time t. Great. And so now I'm going to let h go to 0 while using the fact, right? So by second derivative fact from before, let me call it like second derivative property. Well, I really just mean this kind of tiny result we derived before getting to this point using the Taylor series. So by this fact, the left-hand side, this converges to the second derivative with respect to x of u at xn. Right, and so on the left-hand side, I have the second derivative with respect to x. On the right-hand side, I have this constant rho divided by tau times the second derivative with respect to u. And so that's it, right? So this tells me then that, therefore, uxx at this fixed point is equal to utt times this constant, sorry. At this fixed point. Right, and so since this is true for any point, we expect this equation to hold, right? So this is the derivation. Right. Right, and so you can see this was not like necessarily an easy derivation. Like it was definitely a lot less straightforward than in the case of the transport equation. So a lot of the times, like really understanding where these equations come from and how they connect to physical properties is somewhat involved, and it's typically a combination of ideas from physics, like Newton's second law, and also ideas from math. Like we have this approximation result involving the second order derivatives, which is just pure math. And we were kind of combining these together to get the equation. And so the arguments typically look a lot like this. Okay, and so that's the wave equation in one dimension. I just want to briefly discuss what happens in higher dimensions. For example, dimension 2 and 3. Right, so now you want to, I'm just gonna write down the equation. And so this equation describes like wave-like phenomenon, but now in space rather than just on, relative to a line. And so let me just do the 3D case. The 2D case is similar. So the wave equation takes the form where my function u is now a function of 4 variables, right? I have a point in space and then my time variable. So it looks very similar, right? So I have the second derivative with respect to time. And this is always equal to, of my function u, this is always equal to some number c squared times, well, now I don't just have second derivative with respect to x, I have the sum of all the second derivatives with respect to each particular variable. And so in particular, I get second derivative with respect to x of u, plus second derivative with respect to y of u, and plus second derivative with respect to the third variable z of u. Right, and so as a more compact way to write this is utt is c squared times uxx plus uyy plus uzz. And so this describes like wave-like phenomenon in 3 dimensions rather than just 1 dimension. And the derivation, I think, is very similar. We're not gonna do that, right? But at least it's this equation is now motivated by what we know from the 1-dimensional case. You would expect this to also describe wave-like phenomenon in higher dimensions, and that turns out to be the case. Right, and so this quantity on the right-hand side shows up very frequently in the study of partial differential equations, and in particular, we're going to see it in the next equation we look at in a few minutes. So this is called the Laplacian of U. Right, so this is the right, and so this is in 3 dimensions. And so usually the way we write this as a shorthand is just a triangle applied to U. And so by definition, this is a differential operator. The differential operator is second derivative with respect to x plus second derivative with respect to y plus second derivative with respect to z. Right. So that's the Laplacian in 3 dimensions. In 2 dimensions, the Laplacian is just, well, you only have x and y, you don't have a z, so it's just derivative with respect to x plus derivative with respect to y, second order. Okay. And so an even more compact way to write the wave equation in both 2 and 3 dimensions is just utt is equal to c squared times Laplacian of u. And so that's so if you look up, for example, like the wave equation on Wikipedia or something, it'll probably be written like this. Right. Okay, and so for the final part of the lecture, we're just going to look at one last equation, which is going to be something called the diffusion equation. Which turns out to be another very important PDE, which we'll be spending a lot of the semester studying. Right, and so what does the diffusion equation describe? So let's imagine some body of water, like maybe a big tank of water, or like maybe, if you want to think smaller, maybe just a glass of water or something like that. And suppose that some concentration of dye has been placed in the water. Right, so maybe I have some big tank like this. We're gonna look at a 3-dimensional example for this, so it'll be in 3D. Right, so maybe there's some body of water here, and so imagine maybe I have some concentration of dye which has been placed in the middle, and as time evolves, the dye sort of spreads out like that, right? Right, so dye spreads out over time. Right, and so this phenomenon is what is typically referred to as diffusion, right? Right, the dye is diffusing throughout the water. And so we're going to derive a partial differential equation that describes this phenomenon. If you don't want to think about dye and water, another thing you can think of is just you have a cup of coffee and you place like a drop of half and half at the center of the coffee. Well, the milk is going to spread out over time, and it's going to follow the same basic physical laws or properties as what we're talking about here. Right? So that's another way to think about this. Right, and so how do we make this more precise? Well, now we're in 3D, right? So if I pick a particular point in my tank, it's going to be a point of 3 coordinates, x, y, and z. And so I'm going to let a function u at each point x, y, and z, and then at time t, be the concentration of the dye at the point x, y, z, and at time t. Right, so maybe at time when t is equal to 0, there's just the drop has just been placed in the tank, and then as time evolves, the the dye is spreading out, so the concentration at each point changes, right? So that's what this function describes. And so the claim is that I can describe this phenomenon with the following equation. So if I take the first derivative of u with respect to t, then this is equal to some constant k times the Laplacian of u, where the Laplacian of u involves all these second order derivatives as we defined up here. Right, and so here k is just some physical constant. Right, so it's related to like the properties of the dye or the properties of the liquid and the container and things like that. So there are some scenarios, again, in application where maybe this function k, this constant k is actually a function and not a constant. We're just going to consider the case where it's a constant to simplify things a little bit for now. Right. And right, so what we're going to do now is finally derive this equation, and then we'll be done for the day. And so it's going to turn out that this derivation is hopefully a little bit more straightforward than for the wave equation. And so we're going to use the following physical assumption. Again, you have to have some input from physics. Right, this is sometimes referred to as Fick's law. And the assumption is that the change in the amount of dye in a particular domain, for example, a small ball, let's say the change of amount of dye in small ball B over time, well, it's going to be proportional to the flux through the boundary of the ball, or through like the amount of dye leaving the boundary. Right, so what does this mean? Well, I have some ball B. Imagine this is like a tiny ball that you place inside the domain, and maybe I have some dye that's kind of spreading out in this direction, and maybe a lot of it is leaving through the boundary. Well, that means that if a lot of it is leaving through the boundary, you would expect the concentration to be maybe decreasing, or maybe if it's entering through the boundary, maybe the concentration is increasing. So that's kind of a reasonable assumption. And then Fick's law, which comes again from experimental physics and observation, is that, well, that should be the amount of, or sorry, the rate that the concentration is changing over time, or sorry, the rate that the amount is changing over time. Those are two different things. So the rate that the amount is changing over time should be proportional to this flux, or proportional to the amount that's leaving the boundary, right? Okay, and so here we're going to have to remember some things from multivariable calculus, which we talked a little bit about during our first Zoom meeting. And so let's say this is my ball B. Remember that I'm going to use n to denote the normal field, vector field to the boundary. Right, and so what is the flux? I put this in quotations. So we can mathematically describe the flux by integrating along the boundary of B the gradient of my concentration dot product with n ds, right? So this is a surface integral on the boundary, right? Where again, U is the concentration in the ball of the dye. Right, and so again, so why does this describe the flux? Well, remember the gradient of U measures in some sense how the concentration is changing, and as you change the spatial variable, right? So if I move x, y, z a little bit to the right or a little bit to the left or in some other direction, how does the concentration change? And then taking the dot product with the normal component tells you like how much of that is like going through the boundary, right? Because the normal component is the direction that leaves the surface of the ball, right? So this is kind of measuring the contribution of how much of the dye is leaving through the boundary. And why are you integrating? Well, you look at this at each tiny point, and you want to add up these points over the whole boundary, so you need to use an integral to do that. Right, and so by Fick's law, we're gonna this quantity is going to show up, right? So we have the law says that the change in the amount of dye over time should be proportional to this quantity or this flux. So this is going to be equal to some constant times the change in time of the amount of dye in the ball, right? And so what we need to do finally in order to actually write down a full equation is to just describe, well, what is the amount of dye in a small ball mathematically? And so I want to write down a formula for the amount of dye in the ball B at time t. Right, so let me denote this by m of t, m for like mass or something. Right. Well, recall that my function u at x, y, z, and t is measuring a concentration, right? And so concentration is like the amount divided by, like, say, unit volume, right? So amount per volume. Right, and so kind of very similar to what we did when we looked at the transport equation, you can describe the total amount of dye by integrating the concentration, right? So it turns out that m of t is going to be equal to the integral of u. Since we have three variables, we need to use a triple integral over the ball B of u of x, y, z, t, dx, dy, dz, right? And so again, how do we make sense of this? This is like the concentration. So this is like a amount divided by amount over volume. But then this dx, dy, dz quantity is like a volume, right? So when you multiply them together, the volumes cancel out and you get the total, you get something measuring the amount. This is only valid in like a tiny region of space, but the way to make this more precise is you can add up all these regions by integrating, and so that's where this formula will come from. If you want me to go into this more precisely in detail, maybe I can do this during the Zoom meeting, like review how you would get this formula. Right, and so what does Fick's law say? Well, Fick's law doesn't just say the amount is proportional. It says the change in the amount of dye over time in the ball is proportional to the flux. And so what is the change over time? It's just the derivative with respect to t. So d dt of m of t should be equal to some constant k, whatever the proportionality constant is, times the flux. And so the flux is the derivative on the integral on the boundary of b of the gradient of u dot n. Right, and so now we're going to use this fact that, well, we'll assume our concentration function is continuous, which is a reasonable assumption because like the dye is spreading out continuously. It's not like jumping around and disappearing instantaneously or anything like that. And so that means that I can bring the derivative inside the integral. And so if I look at d dt of m of t, this is the same thing as taking the triple integral on the ball of the derivative with respect to t of u. T. Right, so I have a triple integral of my time derivative. And so on the right-hand side, I have this more complicated surface integral, which is in general hard to analyze because surface integrals are very complicated. But remember that if we have a surface integral of the right form, we can always look at this as, in terms of by using the divergence theorem to convert it to a triple integral. Right. And so if I apply the divergence theorem, well, I'm not really doing much math. I'm just remembering what the theorem says, and I don't have to do anything else really at this point. So if I integrate over the boundary, this quantity, which is the flux, or which is measuring the flux, this is always equal to the triple integral in B of the divergence of whatever this field is, right? So I'm applying the divergence theorem with my vector field F is the gradient of U. And so here I have gradient dot gradient of U. Right? And so what does this mean, right? Let's just like write out, I'm using a lot of symbols here. Well, the gradient of U is just the vector field UX, UY, UZ. And I'm looking at this gradient dot product, or this divergence operation applied to this field. And so this is just, well, I take d dx of ux plus d dy of uy. By definition, that's what this gradient dot product means, plus d dz of uz. And so I just get the sum of all the second order derivatives, right? So this is just uxx plus uyy plus uzz. And so that's just the Laplacian of u that we get on the right-hand side. Right, and so now combining these two ingredients, what do we get? Again, this is using Fick's law on top of these theorems from vector calculus. So we get triple integral on the ball B of second derivative with respect to t, or sorry, first derivative with respect to t, is equal to the triple integral on the ball B of the Laplacian times some constant k. Right, so I have some constant k times Laplacian of u. Right, so again, this is Fick's law plus divergence theorem. Right, so over here we have a little bit of Fick's law is something coming from pure physics. And then the divergence theorem is something that's just pure math, right? And so, well, what am I going to do now? I'm going to, well, let me subtract over the other side, subtract the term on the right from bring it over to the other side. And so remember that if you take a difference of integrals over the same domain, it's the same thing as integrating the difference. So this implies that if I look at the triple integral on the ball B of ut minus Laplacian u, or it's like some constant times Laplacian of u, that this has to equal 0. So notice we haven't used any property about the ball B except that it's a ball. And so this is for any ball. Right. And so now we're almost done. Now we're finally going to reduce matters to the following theorem, which all right, well, let me first tell you what the theorem is. And so suppose that if I take the triple integral on a ball B of some function g, and suppose this is 0 for all balls B, the theorem is that the function g has to be identically 0. And so what we're going to do is apply this theorem to the function g is going to be the difference here. Right, well, we just derived using the discussion from before that if I integrate this function over any ball, then I always get 0. And so as a consequence of this theorem, this tells me that the term inside the integral above has to be 0, right? So setting g equals ut minus k Laplacian u implies that ut minus k Laplacian u has to equal 0. And so therefore, we get the diffusion equation, right? So therefore, ut is this whatever this constant k is times Laplacian u. Right. And so that completes the derivation with the exception of maybe proving this theorem. So this is sometimes, I think in the book, they call this the vanishing theorem. And so what I'm going to do is either prove this in the Zoom meeting on Tuesday or Thursday, or maybe I'll just type up a proof and send you a handout so you can see it for yourself, like how this is actually, why this is actually true. It's not too hard to prove, but we're mostly out of time for today. Right, I mean, the idea is, well, right, let's say I have a point here, this is my point XYZ, and this is, say, B1. Well, if I keep integrating on, this is B2, B3, if I keep integrating on smaller and smaller balls, I'm basically going to just recover only information near the point. And if all of those integrals are zero, the only way this can happen is basically if the function is just zero. That's not a rigorous proof. For the more complete argument, again, maybe I'll send you a handout, or we'll discuss it during one of the Zoom meetings if you'd like. It's actually mentioned in the appendix in the book, but they don't prove it in the 3D case, which I think is kind of unfortunate. So I'll try to at least send you a PDF, I guess. All right, so that's it for today. We'll do some summary and review of what we did in this lecture at the beginning of the next lecture, and then we're going to actually move on and start focusing on the wave equation and trying to actually find solutions to it.